It started with a speck of light, a dot so faint and distant that, for centuries, it was hidden from human eyes. But then came the James Webb Space Telescope. With its vast golden mirror and infrared vision reaching back in time, it saw something astonishing. Something so unexpected, so mind-bending, that scientists across the world paused, recalibrated, and looked again. What it found doesn't just challenge what we thought we knew. It might actually poke holes in the very framework of Einstein's theory of general relativity. Einstein's equations have stood the test of time for over a century. From black holes to time dilation, GPS systems to gravitational lensing, his work has helped shape our understanding of space, time, and gravity itself. But recent observations from the James Webb Telescope are presenting phenomena that seem too odd, too early, or too massive to fit neatly into that framework. This isn't just a scientific curiosity. It's the kind of discovery that could force a complete rewrite of the physics textbooks. Imagine galaxies forming just a few 100 million years after the Big Bang, fully structured, rotating, and enormous. That's what James Webb has been seeing. These galaxies shouldn't exist that early. According to the standard model of cosmology, there simply hasn't been enough time since the Big Bang for matter to coalesce into such large, mature galaxies. Yet, there they are. Webb's deep field images have captured fully formed galaxies that rival or surpass the size of the Milky Way, existing at redshifts that correspond to a time when the universe was only 300 to 500 million years old. This is the first crack in the glass. Because if those galaxies are real and the data holds up under scrutiny, then our models for how the universe evolved might be fatally flawed. The standard lambda cold dark matter model, often called lambda CDM, predicts a slow, hierarchical buildup of structure. Small clumps of matter form first, then gradually merge into larger galaxies over billions of years. The James Webb Telescope, however, is showing evidence of massive, complex galaxies forming far too early, too fast, and in ways that shouldn't be possible if the current models were fully accurate. And then there's the matter of dark energy and cosmic expansion. According to general relativity, the universe's expansion rate is governed by the density of matter and dark energy. But here's where it gets even stranger. The structures being observed are not only forming too early, they also seem to defy expected growth patterns. It's as if gravity is working differently than predicted. Some researchers are beginning to question whether general relativity, or at least its current application at cosmological scales, needs refinement. One of the key puzzles comes from gravitational lensing. This phenomenon, where massive objects bend the path of light due to gravity, is a beautiful confirmation of Einstein's theory. But the James Webb Telescope has spotted lensing events that seem more powerful than they should be. In some cases, the lensing strength implies that the lensing galaxies or clusters are significantly more massive than their visible matter suggests. This could be due to an overabundance of dark matter, or it might mean we're misunderstanding how gravity behaves over vast distances. These observations are leading some scientists to explore modified gravity theories, like MOND, modified Newtonian dynamics, or entirely new frameworks that extend or replace general relativity on large scales. These are controversial ideas, long pushed to the fringes of astrophysics, but the mounting anomalies revealed by the James Webb Telescope are pulling them back into the spotlight. Even the cosmic microwave background, the afterglow of the Big Bang, is being reinterpreted in light of these discoveries. If massive galaxies were already in place this early, then the fluctuations we see in the CMB may have different origins or implications than we thought. Could inflation have happened differently? Was the early universe somehow denser or clumpier than our current models assume? And then there's the issue of time itself. Some theoretical physicists are beginning to flirt with the idea that time might not have been linear or consistent in the early universe, that perhaps time moved differently in the high-energy, high-density moments after the Big Bang, which would throw a massive wrench into our interpretations of early formation timelines. If time itself expanded or behaved in a non-uniform way, then our dating of early galaxies might be off, or our whole concept of cosmic time might be flawed. One of the most jarring realizations is that these aren't just one or two outlier galaxies. The James Webb Telescope has detected several of them, too many for coincidence, too consistent to dismiss as anomalies. These galaxies don't appear chaotic or rudimentary. Instead, They're organized, with well-defined structures, spiral arms, and in some cases, indications of rotational dynamics. That level of complexity isn't something that should appear so early in the universe's timeline. This is what's keeping scientists up at night. The data isn't just strange, it's systematically strange. Some of these galaxies are showing star formation rates that defy expectations. In a universe only a few 100 million years old, there shouldn't be enough time for large populations of stars to form, especially not in such dense clusters. Yet, what Webb is seeing suggests vigorous star formation on a massive scale. It raises fundamental questions about how gas cooled, collapsed, and ignited into stars at such an accelerated pace. Either the conditions of the early universe were wildly different from what we thought, or there are pieces of this puzzle that we still don't understand. Black holes are another point of concern. The early universe seems to have been teeming with them, not just small, newborn black holes, but supermassive ones, weighing millions or even billions of times the mass of our sun. Under the current model, it takes billions of years for black holes to grow that large through steady accretion and mergers. But Webb has discovered quasars powered by supermassive black holes that existed when the universe was less than 1 billion years old. That's too fast. Far too fast. It either means black holes were born massive, or they had a growth mechanism that's still unknown to modern physics. This flood of data is forcing cosmologists to revisit foundational assumptions. Maybe dark matter behaves differently in the early universe. Maybe dark energy wasn't constant. Maybe there's another force or field we haven't accounted for. Some are even suggesting that we consider multiverse models, where different regions of space-time have varying laws of physics. While speculative, these ideas are now being explored with more seriousness than ever before, because the alternative is ignoring hard observational evidence. There's also the growing mystery of entropy and thermodynamics in the early universe. If galaxies were forming this quickly and efficiently, it suggests an extremely rapid increase in complexity and order. That seems at odds with the natural progression of entropy, unless some unknown mechanism was allowing this sudden structuring of matter and energy. Could quantum processes have played a larger role than we imagined? Or is our understanding of entropy on a cosmological scale incomplete? Some theorists are going even deeper, proposing that the fabric of space-time itself might have emergent properties. That space and time aren't fundamental, but arise from more basic quantum phenomena. This idea, often explored in theories like quantum gravity or loop quantum cosmology, suggests that gravity and time could behave differently under extreme conditions. The early universe, being so dense and energetic, might have triggered behaviors we don't see in the calm, expanded cosmos we inhabit now. Even our ideas of the Big Bang are being revisited. If the first galaxies and black holes formed earlier than expected, then the timeline of the Big Bang might need adjustment. Some scientists are investigating whether what we call the Big Bang was a singular, clean beginning, or whether it was just one phase in a more complex cosmic cycle. Could the universe have gone through previous expansions and contractions? Could the current expansion be just the latest act in a much older cosmic drama? James Webb's discoveries are not just rewriting the beginning of the story. They're questioning the structure of the story itself. The telescope was built to look further back in time than ever before, and it did. But instead of seeing the slow dawn of cosmic order, it revealed a universe already bustling with mature structures, bursting with energy and organization. This wasn't supposed to happen. Not yet. Not this soon. The implications ripple out in every direction. If galaxies formed faster, if black holes grew earlier, if light was being bent more dramatically than predicted, then we may be underestimating the complexity of the universe by several orders of magnitude. That realization shakes not just general relativity, but our entire scientific worldview. General relativity has been tested in countless ways and has passed with flying colors. From the bending of starlight during eclipses to the warping of time measured by atomic clocks on GPS satellites, Einstein's equations have proven incredibly robust. But those tests are local, solar system scale, or at best, galactic. What James Webb is doing is testing those ideas on a scale that stretches across the cosmos and deep into the past. And it's there, in those vast ancient realms, that the theory may be showing its limits. These limits don't necessarily mean Einstein was wrong, just as Newton's laws were not wrong, but rather incomplete when viewed at high speeds or strong gravitational fields. general relativity may also be a piece of a much larger framework. Einstein himself believed his theory wasn't the final answer. He spent decades trying to find a unified field theory, a deeper explanation that could unite gravity with quantum mechanics. He never found it. And to this day, that quest remains one of the greatest unsolved problems in physics. The James Webb Space Telescope could be the key that unlocks that door. Its unprecedented ability to observe in the infrared allows it to see light that has traveled over 13 billion years to reach us. In doing so, it's not just showing us what the early universe looked like. It's giving us new clues about the rules that governed it. Maybe gravity itself was different. Maybe space-time wasn't yet stable. Or maybe the emergence of structure, galaxies, stars, black holes, operated on principles we haven't yet discovered. Even more fascinating is how these observations are influencing other areas of physics. Quantum physicists are starting to look at Webb's data and ask whether some of the anomalies could be explained by entanglement on cosmic scales or by holographic principles suggesting that the universe might be a projection of information encoded on a boundary. It sounds like science fiction, but these are serious theories being discussed in serious papers. We are at the frontier of a potential paradigm shift. And like all revolutions in science, it begins with uncomfortable questions. The scientists who built and operate the James Webb Telescope never expected the early universe to be so richly populated, so quickly evolved. They anticipated seeing the gradual emergence of light and structure from a murky, post-Big Bang darkness. Instead, what they found was a cosmos already pulsing with complexity, seemingly skipping steps in its own evolution. This is why scientists are worried, not in the sense of fear, but in the sense of awe. The kind of worry that comes when the universe you thought you understood suddenly starts behaving in ways you can't explain. It's not just about tweaking numbers in an equation, it's about potentially rewriting the very story of how everything came to be. From the smallest particles to the largest galactic clusters, from the birth of time itself to the nature of reality. Yet, this is also the most exciting moment for science. These are the moments where breakthroughs happen. When the data no longer fits the model, it means the model is ready for change. And every great leap in scientific understanding has begun with this kind of moment. Copernicus realizing the Earth wasn't the center. Newton discovering gravity. Einstein redefining time and space. Perhaps now, it's our turn to witness the next chapter. So, as the James Webb Telescope continues its mission, peering deeper into the universe, capturing the faint whispers of ancient galaxies. One thing is clear, the cosmos is far stranger, faster, and more complex than we ever imagined. The universe has kept its secrets for billions of years, but now, piece by piece, it's revealing them. And what we learn next could change everything we thought we knew about where we came from and where we're going. Because when the universe speaks in light older than time, we have no choice but to listen. And sometimes, what it says changes the very language of science itself.